You know, I've spent my whole life trying to get people to see things as they actually are. Not as they were told they are, not as they feel like they should be, as they actually are. And one of the things that drives me absolutely crazy, and I mean this, is the word cold. Because cold doesn't exist. I'm not being clever. I'm not doing a physicist trick where I redefine words to win an argument. I mean it literally. Cold is not a thing. You cannot make it. You cannot bottle it. You cannot throw it across a room. When you open a freezer door and you feel that rush on your face, that is not cold coming out. That is heat going in. And if you think that's just a small distinction, a matter of semantics, then you've missed something enormous about the way the universe is put together. See, most people walk through their entire lives with a completely backwards picture of what's happening when things get hot or cold. And it isn't their fault. Nobody ever stopped to show them the real thing underneath. They got the shortcut, the comfortable lie, the version of physics that gets you through the school exam but leaves you fundamentally confused about reality. I don't like that. I never liked that. So here's what we're going to do. We're going to start from scratch. We're going to pull apart everything you think you know about heat and cold until it stops making sense. And then, and this is the fun part, we're going to put it back together the right way. And I promise you, by the time we're done, the world is going to look a little different to you. Not smaller, bigger, stranger, more interesting than you thought it was this morning. That's what real physics does. It doesn't close things down, it blows them wide open. So let's begin. Start with something you've done 1,000 times. You pick up a metal spoon that's been sitting on the counter. Then you pick up a wooden spoon sitting right next to it. Same room, same counter, same air temperature surrounding both of them for the last 8 hours. The metal one feels cold. The wooden one doesn't. Now, if cold were a real thing, if it were a substance, a property that lived in objects, something they possessed, then you'd have to explain why the metal has more of it than the wood. They've been sitting in identical conditions, but your hand tells you they are different. Your hand is measuring something. What is it actually measuring? It's measuring how fast heat is leaving your hand. That's it. That's the whole trick. Your skin doesn't measure temperature. It measures heat transfer rate. The metal pulls heat out of your fingers faster than wood does. That's why it feels colder. Not because it is colder. It isn't. They're the same temperature. But because it conducts thermal energy away from you more efficiently. Your nervous system evolved to detect heat loss as a survival mechanism. And somewhere along the way, we all agreed to call that sensation cold. And then we made the catastrophic mistake of thinking the word pointed at a real thing in the world, rather than a relationship between two things. This matters. Let me show you how much. Here's what's actually happening at the scale where physics lives. Everything. Your hand, the spoon, the air in the room, the freezer, the sun, is made of atoms. And those atoms are not sitting still. They are vibrating. They are bouncing. They are moving in ways that would look, if you could see them, like the most chaotic, violent, extraordinary dance you've ever witnessed. A single cubic centimeter of air at room temperature contains about 27 quintillion molecules. That's 27 followed by 18 zeros. And every single one of them is moving at an average speed of around 500 meters per second. That's faster than a rifle bullet. And they're colliding with each other billions of times per second. Temperature is not a property. Temperature is a description of that motion. Specifically, it's proportional to the average kinetic energy of those molecules. High temperature means fast-moving particles. Low temperature means slow-moving particles. When we say something is hot, we mean its atoms are vibrating vigorously. When we say something is cold, we mean its atoms are vibrating sluggishly. Hot and cold are not two different things. They are 2 points on one single spectrum, the spectrum of molecular motion. And heat, the thing that actually flows, the thing that actually exists as a transferable quantity, heat is what we call the energy that moves from faster-moving particles to slower-moving particles when they're brought into contact. Notice what I just said. Heat moves from faster to slower, from hotter to colder, always in that direction. You never see it go the other way spontaneously. You never see a warm cup of coffee get hotter while the table it's sitting on gets colder. The energy flows downhill, so to speak, from where there's more of it to where there's less. Cold is not flowing in the other direction. There is no other direction. Cold is not flowing anywhere because cold is not a thing that flows. What you're observing every single time you experience cold is an absence of vigorous molecular motion and the movement of heat away from you toward that region of lesser motion. Now here's where it gets interesting, because you might say, fine, that's a clever way of looking at it, but it doesn't really change anything practical. The freezer still freezes things, ice still melts, your hand still feels cold when you grab the metal spoon. What difference does it make how I describe it? And I would tell you, it makes all the difference, because a wrong picture leads you astray the moment the situation gets complicated. And situations always get complicated. Let me give you a case. For most of human history, we're talking roughly until 1850, give or take, the dominant theory of heat was something called caloric theory. The idea was that heat was a real substance, an invisible fluid. It had weight. People actually tried to measure that weight, and some thought they found it, which tells you something about the seductive power of wrong ideas when they fit your intuitions. This fluid, caloric, flowed from hot objects to cold ones. When you burned wood, you released the caloric stored in it. When you heated metal, you were adding caloric to it. The theory wasn't stupid. It explained a lot of everyday observations rather well. Heat does flow from hot to cold. Things do change when you add heat. The metaphor of a fluid has a certain appeal. But then people started building steam engines. And when you build a steam engine, you have to think carefully about what you're actually doing. You're not just watching heat flow, you're converting it into work. You're making a piston move, and caloric theory had a deep problem with this. If heat is a fluid, a substance, then how does it become motion? Where does the substance go? James Joule, a British brewer, not even a professional scientist, which I love, did a beautiful series of experiments in the 1840s. He had a paddle wheel in a bucket of water connected to falling weights. The weights fell, the paddle turned, the water got warmer. He measured everything with extraordinary care. The amount the water warmed up was precisely, quantitatively, predictably related to the distance the weights fell. He kept getting the same number, 4.18 joules of mechanical energy to raise 1 gram of water by 1 degree Celsius. Every time, without exception. That number is now called the mechanical equivalent of heat, and it killed caloric theory dead. Because what Joule showed was that heat isn't a substance that gets conserved. Heat is energy. It's the same stuff as the energy of the falling weights. It's the same stuff as the energy of a moving billiard ball. It converts. It transforms. It's interchangeable with other forms of energy at a fixed and measurable rate. And this is not a philosophical point. It's an experimental result with a specific number attached to it. Once you understand that, you understand something that caloric theory never could. A steam engine isn't magic. It's not creating something from nothing. It's taking the disordered motion of hot gas molecules, motion going in every random direction, and partially extracting it, funneling some of it into the ordered motion of a piston going in one particular direction. The efficiency is limited, always, by deep and fascinating constraints we now call thermodynamics. But the mechanism is clear. Heat is molecular motion. Work is directed mechanical motion. They're the same thing in different organizational forms. Let me take you somewhere colder, really cold. Suppose I keep removing energy from a substance. I cool it down and down. The molecules slow. The vibrations diminish. How far can I go? Well, if temperature is molecular motion, then there's a minimum possible temperature, the point where all motion stops. Zero motion. Zero kinetic energy. You can't go lower than that, because you can't have less than no motion. That temperature is called absolute zero. It's minus 273.15 degrees Celsius, or zero on the Kelvin scale, which is a thermodynamic scale built with this point as its foundation. William Thomson, Lord Kelvin, figured out this limit in the 1840s and 1850s by analyzing the behavior of gases and extrapolating to see where they'd have zero volume and zero pressure if you could get there. Here's what absolute zero means if you take the molecular picture seriously. It's not just very cold. It's a fundamental physical boundary. It's the edge of the temperature axis. Below it, there is nothing. Temperature below absolute zero is not a thing, the same way a speed faster than light is not a thing, the same way a probability greater than 1 is not a thing. And here's what I find beautiful about this. Cold, as a concept, doesn't have a corresponding fundamental limit on the other side. There's no maximum hot, no absolute ceiling on temperature, the way there's an absolute floor. The hottest temperatures we know of, inside a nuclear weapon detonation, in the first fractions of a second after the Big Bang, are around 10 to the 32nd Kelvin. That's 100 million trillion degrees. And there's nothing in the physics that says you can't go higher, at least in principle. So even if you wanted to preserve the idea that hot and cold are symmetric opposites, you can't. The universe is built asymmetrically. There's a zero. There's no ceiling. They were never opposites. One of them is a direction, and the other is a wall. Now I want to tell you something that surprises people. Even at absolute zero, or rather, approaching absolute zero as closely as quantum mechanics allows, things are not entirely still. There is something called zero-point energy. It comes from the uncertainty principle, which Heisenberg worked out in 1927. The principle says you cannot simultaneously know both the position and the momentum of a particle with perfect precision. The more precisely you pin down where something is, the less precisely you can know how fast it's moving, and vice versa. This is not a statement about measurement limitations. It's a statement about what exists. The particle genuinely doesn't have a perfectly definite position and a perfectly definite momentum at the same time. That combination of properties simply isn't available. What this means for temperature is remarkable. If a particle were at absolute zero, perfectly still, zero momentum, you'd know its momentum exactly, zero, which means, by the uncertainty principle, you'd have zero knowledge of its position. It could be anywhere. That's contradictory if the particle is supposed to be sitting in a specific place in a specific crystal lattice. So particles can never fully stop. They have an irreducible minimum jitter built into the fabric of reality by quantum mechanics. Liquid helium at atmospheric pressure never solidifies no matter how cold you make it, because this quantum jitter is enough to keep the atoms mobile. You need to apply pressure, around 25 atmospheres, to force it into a solid. The zero-point motion is not nothing. It's a measurable, engineered around, real effect. This is where explanation reaches its fundamental limits. Why does the uncertainty principle hold? We can derive it mathematically from the structure of quantum mechanics. We can verify it experimentally, and we have, with extraordinary precision. But why is the universe built this way? Why is there an uncertainty principle at all? I don't know. Nobody knows. That's not a failure. That's where bedrock is. You dig until you hit something you can measure, but not explain in terms of something simpler. And then you say, This is where it ends. This is fundamental. There's one more thing I want to show you because it connects everything. You know why a refrigerator works? Not the vague story, the actual thing. Inside your refrigerator, there's a fluid, a refrigerant, that circulates through a loop. On the inside of the fridge, this fluid is allowed to expand and evaporate. When a liquid evaporates, when it turns from liquid to gas, it absorbs energy from its surroundings. The fastest moving molecules escape the liquid surface and carry their energy with them. The liquid left behind is cooler. This is why sweating cools you. This is why blowing on hot soup helps. You're enhancing evaporation. So on the inside of the fridge, the refrigerant evaporates and absorbs heat from the air and the food inside. Then a compressor, that thing you can hear humming, compresses the gas back into a liquid. When you compress a gas, you increase the molecular collisions, you increase the motion, you raise the temperature. The now hot liquid runs through coils on the outside of the fridge, the ones on the back, and it dumps that heat into your kitchen. Then it expands again inside, gets cold again, absorbs more heat, gets compressed again, dumps it outside again. Your refrigerator is not making cold. It is moving heat. It's a heat pump. It takes thermal energy from inside the refrigerator and pushes it, using electrical energy to run the compressor, into your kitchen. That's why your kitchen gets slightly warmer when you run your fridge. That's why opening a refrigerator does not cool a room. If you leave the door open long enough, the kitchen actually gets warmer, because the compressor is adding work energy into the cycle, and that energy goes somewhere. Cold is not being manufactured in there. Heat is being relocated. And this is the underlying truth behind every cooling technology we've ever built. Air conditioning, refrigeration, cryogenic equipment for physics experiments, the systems that keep your computer from melting, all of it. They are all, every single one of them, heat movers. They take thermal energy from somewhere you don't want it and deposit it somewhere you mind less. You cannot make cold. You can only relocate heat. That's all we've ever done. That's all we can do. So let's come back to where we started. That rush of air from the freezer hitting your face. You now know what's happening. The air inside the freezer has very little thermal energy. The molecules are moving slowly. When that slow-moving air meets your skin, heat flows from you into it. The faster molecules of your body transfer energy to the slower molecules of the cold air. Your nerve endings detect the loss of heat and send a signal to your brain, which interprets it as cold. There is no cold substance striking your face. There is heat leaving your face. There is an absence of vigorous molecular motion on one side of the boundary, and the universe's relentless tendency to equalize, to spread energy from concentrated regions to dilute ones, doing exactly what it always does. The thermodynamic arrow is always pointing in the same direction. Energy spreads out. Motion equilibrates. Order, in the thermal sense, is unstable. The universe doesn't push cold at you, it pulls heat away from you. And you feel that pull, and you call it cold. And you've been doing it your whole life without knowing what you were actually describing. The real lesson is not just about cold. The real lesson is about what it means to understand something. Caloric theorists could tell you that heat flows from hot to cold. They could make predictions. Some of their predictions were right, but the picture was wrong, and when they pushed it to places it hadn't been pushed before, the steam engine, the relationship between work and heat, it broke. Joule didn't just give us a number. He gave us the beginning of the first law of thermodynamics. Energy is conserved. It converts. It transforms. It is never created or destroyed. And you can't know that from inside the caloric picture. Physics isn't just about getting the right answers on the questions you already know to ask. It's about building a picture of reality that is reliable enough to answer questions you haven't asked yet. A picture that doesn't break when you push into unfamiliar territory. The molecular picture of heat, temperature as motion, heat as energy, cold as the relative absence of both, that picture holds. It held when we built refrigerators. It held when we probed absolute zero. It held when quantum mechanics forced us to revise it at the very bottom. And even then the revision was an extension, not a replacement. Cold is not the opposite of heat. Cold is a direction. It's the direction of decreasing molecular motion, decreasing thermal energy, decreasing temperature. And the fact that direction has an end, absolute zero, the wall, the floor of the universe's temperature, while the opposite direction, the direction of more heat, more motion, more energy, has no corresponding ceiling. That asymmetry is not an accent of language. It's a feature of reality. And you can see it, now that you know where to look, in every ice cube you've ever held, every metal doorknob that felt cold on a winter morning, every time you breathed on your hands to warm them up. The universe has been showing you this your whole life. You just needed someone to point at what was actually there.